Let's begin by exploring the core hardware components of our rehabilitation robot. The control unit is built with a high-performance STM32F746G microcontroller paired with powerful Maxon 20-watt BLDC motors and specialized motor drivers. For precise actuation, we use a 15-bit 0-10-volt I2C DAC module. An ESP32C3 is dedicated to data visualization and the user interface through a locally hosted web app. Together, these components deliver real-time control and robust operation. This slide outlines the interconnection between our system components. The STM32 and ESP32 communicate over I2C, while encoders provide velocity feedback directly to the STM32. Current commands are issued to the motor drivers through the DAC, and remote operation and monitoring are facilitated by the ESP32. Optocouplers and various panel indicators ensure protection and real-time status updates throughout the system. Here, we demonstrate our real-time data acquisition and monitoring capabilities. In the top right corner, the video shows a live torque versus time plot on the web interface connected via Wi-Fi, alongside images of our web interface. Users input their body metrics, weight, height, and gender, which are used to calculate the arm's inertia for precise control. The web app also displays the number of repetitions, identifies the controlling side, indicates the exercise mode, such as rotational or flexion extension, and allows remote adjustments to key system parameters. Our programming leverages C code on the STM32 Nucleo 144 platform to manage basic peripheral control and sensor interfacing. Running within a real-time operating system, RTOS, this approach ensures that the system reliably responds to sensor feedback and user input SORM. Next, we dive deeper into our STM32 coding architecture. The control system is implemented using a real-time operating system, RTOS, running across 3 dedicated threads for motor control, real-time communication, and data recording. This approach ensures the robot responds accurately to sensor feedback and user inputs. In addition, our multi-threaded design integrates essential functions such as the motor encoder interface, PID controller, disturbance observer, reaction torque observer, and the application of a healthy arm torque profile to achieve precise rehabilitation exercises. Following this, we developed our own custom library for the DAC modules. Since no existing libraries were available for this DAC series, we adapted an Arduino-based library for STM32 using a custom I2C protocol. We partnered with DF Robot for sponsorship in exchange for our library development, and our code has even been shared for publication purposes, along with an application note for future reference. Here's a snippet of our custom DAC library. These library files simplify DAC configuration and enable seamless interfacing with the rest of the system. This slide highlights our physical system design and construction. We focused on achieving a relaxed shoulder position through a simple ergonomic layout. The compact design integrates all hardware components, making the system easy to assemble and user-friendly in a clinical setting. Next, we review our designing process through several initial modeling attempts. To ensure a relaxed shoulder position, we implemented both horizontal and vertical adjustments of the motor. Additionally, since our exercises occur in 2 different planes using a single degree of freedom, we developed a mechanism to change the motor orientation. These iterative designs were crucial in refining our approach. This slide features a video of our early simulations, conducted using MATLAB, SolidWorks, and Simulink. The simulation visualizes our initial design, demonstrating how we achieved motor adjustments, executed the exercises, and managed the change of motor orientation for different exercise modes. Here we showcase our final design iteration. The refined design is simple, easy to adjust, and optimized for both performance and ease of construction, reflecting the lessons learned from earlier prototypes. This slide presents our final prototype. In this integrated system, all subsystems, including the control panel, power supply, motors, motor drivers, and battery backup, are combined into a nearly portable standalone unit that only requires a standard power outlet. In this final slide, we illustrate our motor adjustment mechanisms through two videos. The left video demonstrates how simple vertical and horizontal adjustments achieve a relaxed shoulder position, while the right video shows how the motor orientation is changed by 90 degrees for different exercise modes, ensuring natural and effective movement during rehabilitation. To assemble the system, reducing complexity and enhancing convenience, a PCB was necessary. Here you can see a prototype version we used for testing and one of our early designs. By optimizing that design, we finally came up with this very compact design, which is the same size as the STM32 board itself. Now let's move into results and discussions. Here you can see the flexion and extension exercise, where we simulate the hemiparetic condition by keeping the right arm idle. The corresponding position versus time data obtained is in the graph, which shows bimanual coordination. This is the torque versus position graph for the same exercise. Here, the follower torques are much lower than the master torques, but the difference is filled by assistance torque, allowing both arms to move in bimanual coordination. Similarly, this graph shows the position versus time for the internal and external rotation exercise. And here's the corresponding torque versus position graph for the same exercise. In this research, we successfully developed a bimanual rehabilitation robot designed to assist hemiparetic post-stroke patients in their recovery process. Our key contributions include implementation of a bimanual rehabilitation robot, a sensorless torque estimation method, facilitation of two essential rehabilitation exercises in one robot while maintaining a relaxed shoulder position, adaptive resistance based on the torque profile, an easy-to-use interface with intuitive controls, necessary adjustments for improved performance and usability. Moving forward, we plan to conduct experiments with paralyzed patients to further evaluate the system's effectiveness. These trials will allow us to refine our torque profile for rotational motion, ensuring better adaptability and personalized rehabilitation. Our work has been recognized at international conferences. with publications in ERU Symposium 2023 and Mercon 2024. On ERU Symposium 2023, where we received the Best Poster Award. On Mercon 2024, where we won the Best Paper Award in the track of Robotics and Intelligent Systems. These are the references we used. We would like to express our heartfelt gratitude to Advanced Telecommunication Laboratory, Asian Institute of Technology, Robotics and Automation Laboratory, University of Moratuwa, DF Robot Company, China, and all the individuals who have contributed their time, expertise, and support to this project over the course of its development. Thank you.